This is our mechanical workshop. So you can see over here, this is the video of our mechanical workshop. Now in this mechanical workshop we have to go to the HT lab. So this is just showing the way of HT lab. So this is how you can go to the HT lab in our mechanical workshop. So let's see the heat transfer lab, means HT lab. This is it. Okay. Now we will see the instrument on which we want to perform the practical. So let's see our instrument. So you can see it over here. This is our instrument, and the name of the instrument is, yes, you are right, heat transfer from a pin fin. Aim of our practical is to find out heat transfer through pin fin apparatus by natural convection method. So here we are going to solve this practical by natural convection method, and the name of the practical is heat transfer through pin fin. Now let's go and see what is the concept of theory related to this practical. So now first of all, let's see what is the fin. So let me give you one example. Let's say if you have a cup of tea, and in that cup you have a hot tea, and let's say if I will tell you drink that tea in 1 minute, so now that is not possible because tea is very hot, so you cannot drink in 1 minute. But to drink in 1 minute or 2 minutes, what you gonna do? You can take that tea into the one very big pan, and now you can easily drink that tea within a 1 minute or 2 minutes. But why you are able to do that? So because, yes, you are right, because you have increased the surface area. First of all, you have a tea in 1 cup, so surface area is less compared to the very big pan that you have, in which you have a very big surface area. So if you increase the surface area, the rate of heat transfer is increasing. That means how speedily the heat will be transferred. That is what the rate of heat transfer means. So here the additional surface, or whatever the additional surface that you are taking, that is known as fin. So additional surface, or you can say extended surface, is fin. So in some of you might seen the fin attached in automobile engines. Why they are attached that fin over here? Because sometimes the engine got heated, and that is a possibility that will cause the failure of engine. So that's why some additional surface is provided to the engine to increase the rate of heat transfer, so that the engine will stay within a limit. So these extended surfaces, or the additional surfaces which are attached to a device or a wall or a material, is known as fin, to increase the rate of heat transfer. So here you can see that the fin are the extended surfaces which help to raise the rate of heat transfer by convection. We know that Q is equal to H delta T. Now let's see, if someone will say the value of H is fixed, let's say the delta is fixed, delta T is fixed. Now what is the way of increasing the rate of heat transfer, means Q? Yes, you are right, you have to increase the surface area, and that is what the fin is doing. So that is why we provided the fin. So that is the logic. So now so far we have covered what is fin and what is the function of fin. So fin are used in large number of applications to increase the rate of heat transfer. So now you know the function of fin is to increase the rate of heat transfer. Now as we know that the fin is used for increasing the rate of heat transfer, that's why fin material has higher thermal conductivity. Now where the fin is attached, the fin is exposed. Let's say the fin is attached to some material or some wall, and then what is happening? If the fin is exposed to a flowing fluid which is cools or heats it with the high thermal conductivity, allowing increased heat being conducted from wall through fin. So what he is trying to say, let's say there is one wall and you have attached the fin. Fin means additional surface you have attached over there. So now whatever the heat that wall possesses will be conducted through fin, and all heat will be coming to the fin. Why? Because fin have higher thermal conductivity, and from the fin that it will go to the surrounding air. So that is how the whole mechanism is working. So now in this practical we are going to use free convection method, because this practical can be done by two methods, free convection method and forced convection method. But this practical we are going to solve by free convection method, or you can say natural convection method. So in this practical we are going to use free convection method to find out the temperature at a certain length of fin. So that is our goal, that is our purpose. So this is the concept related to fin. Now let us see the image. So in this image you can see the different type of devices which is attached to this apparatus. So first you can see over here is the dimmer. So this is the dimmer which is attached. You can see that by the red bullet over here there is a one dimmer. Through dimmer you can change the value of voltage and current. So you can see there is a voltmeter and there is a ammeter. So voltmeter will show the voltage and ammeter will show the current. And there is one temperature indicator over there. It is a digital temperature indicator. So channel 1 means temperature T1, channel 2 means temperature T2, so and so. And there is a one switch, on and off switch, through which you can make the device on or off. Now you can see that there is one rectangular duct. So there is a rectangular duct over there and there is a top cover. You can see in the figure there is a top cover. So if you see from the top view, from that top cover, from the top cover, you can see there is one metal fin or metal rod over there, which is known as fin. And from the outer side, you can see that the fin is inside the rectangular duct, but you can see that from outside, one end of the fin is connected with the heater. There is one manometer over there, and you can see that the blower at the end of the duct. So this is the duct. At the end of the duct, you will have a one blower. So this is the construction of device. So this is a basic thing. Now let's see it further in detail. So now let's see the construction of device and what we are going to do over here. So as I already told you, in this top cover, if you see from the top view, from this top cover, you can see one kind of metal rod over there, that is known as fin. And here you can see this picture, the heater is, you can see that from the outside. So in the previous PPT, we have seen that the heater is connected on the outer end of the fin. So here you can see that the one end of the fin connected with the heater. Okay. So now this is the same fin which you cannot see from the figure, but here for your understanding, I have mentioned it over here. So here you can see that there is a metal rod, so which is known as fin. So now I will call metal rod as a fin. So here you can see that circular rod, which is metal rod, which you can say fin over here. And this is the total length of fin. The total length of fin is known as capital L. Here heater is attached at the one side of the fin that I already shown you. Now here you can see that at a different length of fin, let's say here at a different length, let's say this is x1 length, this is x2. So at x1 length you have temperature T1, at x2 length you have temperature T2, at x3 length you have temperature T3, at x4 length of the fin you have temperature T4, and at x5 length you have temperature T5. Now let's say at any distance we want to find out the temperature at that point for a fin. So let's say at a length of x, or you can say that at the length of fin x, so this much distance, so the x distance, I want to find out the temperature of T5. So our aim of our practical is to find out the temperature T5 by practically and validating that temperature with theoretically. So here you can see that at a distance x, we have a temperature T5. So what we gonna do? We gonna first find out the value of T5 from practically, and after that we are going to find the value of T5 by theoretically, and let's see what is the value that we are getting. And T6 is the fluid temperature, so that is passing over the fin, so that is known as fluid temperature T6. So this is the construction of device. You have to switch on the practical. This is the voltage meter, ammeter and temperature indicator. This is thermostat through which you can change the value of voltage and current. You can see on the screen. Again, if I am changing the dimmer, you can see the change in voltage and current. This is temperature indicator. Now this is the blower switch. So if you switch on the blower, the air will be passed through the rectangular duct. So air will be passed like this. Now this you can see the change in manometer. If you do this practical by forced convection, now this is the top view of the fin. you can see the top view of the fin over here. So this is the top view of fin. Let's see the practical. So we have put these practical on some voltage and current, and after steady state reach, now we are going to measure the reading. So this is the top view of the fin. This is the heater which is connected to the fin, and voltage and current is given through thermostat to this heater. So now let's read the reading. So this is channel 1, so this is temperature 1. This is channel 2, so this is temperature 2. This is channel 3, that means this is temperature T3. This is channel 4, which is open channel, so that's why it shows the ambient temperature. This is channel 5 and channel 6, which showing the duct fluid temperature. Okay, so which is 35. So this is our total temperature. So if you perform this practical by forced convection, you have to switch on the blower and the air will be passed through this duct. So this is how you can perform the, and you can see the change in manometer over here. Okay, if you do this by forced convection, but we're gonna do natural convection. Now let's see the calculations. So first of all, let us see what is the voltage value that we have fixed. We have fixed the voltage value as 100 volt. We have fixed the current 0.018. After steady state, we have taken the reading something like that. We have a temperature T1 is equal to 68 degrees Celsius, T2 is equal to 66 degrees Celsius, T3 equal to 56 degrees Celsius, and T4 is open channel. So that wire is open, so that's why it's not going to show the temperature. And the temperature which are showing, that is going to be an ambient temperature. So that's why we are not going to consider a channel T4. That means temperature T4 we are not going to be considered. That's why I have written open channel over here. Then we have a T5, which is the temperature 61, and T6, which is fluid temperature, ambient temperature, which is 35 degrees Celsius. So this is the reading that we have. So these all are the readings that we have recorded over here after steady state etching. Okay, so now let's see the calculation. And first we do the calculation. Before that, let's see the whatever the given data. So fin outer diameter is given, which is 12.7 mm. So you have to remember, you have to convert all the value into the meter. So 12.7 mm means 12.7 into 10 raised to minus 3 meter. Then the length of fin is given, which is 102 mm. So it will be 102 into 10 raised to minus 3 meter. Now length of fin at which we want to find the temperature. So that is the distance x, as you can see in the figure. So at a distance x, we want to find the temperature T5. So that distance x is given, which is 8.2 centimeters. So which is equal to 8.2 into 10 raised to minus 10 meter, 10 raised to minus 2 meter. Now the conductivity of the fin is given, which is 54 watt per meter degree Celsius. Now let us find out the mean temperature of the fin. So average fin temperature will be T1 plus T2 plus T3 plus T4 plus T5 by 5. So here we do not have, as I already told you, that T4 is an open channel. So we are not going to consider the channel T4. So we are only going to consider a 4 temperature, T1, T2, T3 and T5. So our average temperature will be T1 plus T2 plus T3 plus T5 divided by 4. So our equation is going to become like this: T1 plus T2 plus T3 plus T5 divided by 4. So which is going to be 62.75 degrees Celsius, because one channel is open. So that's why we are not going to consider that temperature, and that temperature is T4. So we are not going to consider it. So our average fin temperature is 62.75 degrees Celsius. Now what is mean film temperature? So mean film temperature is equal to mean temperature of the fin plus fluid temperature divided by 2. So we have the duct fluid temperature, which is T6, which is 34 degrees Celsius. So the mean fluid temperature will be T mean plus T mean of the fin plus T fluid divided by 2, which is going to be 48.87 degrees Celsius. So if we convert it into the Kelvin, it is going to become 321.87 Kelvin. Now delta T means T mean of the fin minus temperature of fluid. So that is going to become 27.75 degrees Celsius, because T mean that we have got is 62.75 and T fluid, which is 35 degrees Celsius, which is T6. T fluid means T6. So this is going to be 27.75 degrees Celsius. Here delta T I am not going to convert it into the Kelvin. If you convert it into the Kelvin, you will get the same value. So that's why I put it as it is in degrees Celsius. Now beta is known as volume expansion coefficient, which is equal to 1 upon T mean fluid. So 1 upon T mean fluid plus 273. So we have already converted into the Kelvin. So we have direct value, which is 321.87. So 1 upon 321.87, which is equal to 0.0031 Kelvin. Now let us find out the Grashof number. So you know that the Grashof number is equal to G into beta into diameter cube into delta T upon kinetic viscosity square. Now here you can see that you have the value of G, which is 9.81, beta you already have 0.0031, diameter cube, that is you already have fin outer diameter 12.7 into 10 raised to minus 3 whole raised to cube, delta T, which is 27.75 upon kinetic viscosity. Now where to find kinetic viscosity? So there is one table which is known as property of air. So at that table you have to find the property at mean film temperature. So our mean film temperature is 48.87 degrees Celsius. So let us go to the properties of air table. So here you can see that property of air table. So our mean is 48.87. So I can take it nearly equal to 50 because the value will not going to be changed much. But if you have the T mean as 45, then you have to take the average of 40 and 50. But here it is 48.87, so which is nearly equal to 50. So I gonna see this value at a temperature 50. So here you have to see the value of kinetic viscosity at 50 degrees Celsius. So at 50 degrees Celsius, you can see that the last table, which is 70.95. So here you can see that kinetic viscosity multiplied by 10 raised to minus 6. So at 50 degrees Celsius, you have 17.95 into 10 raised to minus 6. So from this table, we got the value at 50 degrees Celsius, kinetic viscosity is equal to 17.95 multiplied by 10 raised to minus 6. So that is what you have to put it over here. And now if you do the calculation, you will get the Grashof number is equal to 5359.60. Some of you might got the values different, like 5364, 5365. That is okay because that is due to the point variation. But it will be 53 around, like something like this. Now Prandtl number. So you know that Prandtl number is equal to QCP upon KR, but that you don't need to calculate again. You can find this value from the properties of a table. So at the T mean field, so T mean field is 50 degrees Celsius. So always remember you have to see the property of air at the mean film temperature, which is 50 degrees Celsius. So at 50 degrees Celsius, PR is 0.698. So that is why here you can see that we have the PR is equal to 0.698. Now let us do the calculation of GR.PR. So we have the value of GR over here, we have the value of PR, do the multiplication, and it comes out as 3741.00. Now I have taken this equation, Nusselt number is equal to 1.10 into bracket GR.PR raised to 1 by 6. But why I have taken this value? Because here you can see that the 3 equation is given, and for our range of GR.PR, it will be less than T raised to 4. So that's why I have picked up this first equation over here. So you have these 3 equation given, and based of the multiplication of GR.PR, you have to see that the value of GR.PR falls in which range. So for that, the first equation is applied for our case. So that's why I've chosen this equation. Nusselt number is equal to 1.10 bracket GR.PR raised to 1 by 6. Now we know that Nusselt number is nothing but the HD by K is equal to, now if you solve this value, so put the value of GR.PR, do the calculation, and you will the right hand side will be comes out as 4.33. Now you have the value of K over here, but how you can find the value of K? So here you have to see the value of K air. So that's K air you have to see at the property of air table. So at 50 degrees Celsius, you have to see the value of K. So that comes out at 0.0283. So put that value over here, and you have the value of D, which is diameter, which is 12.7 mm. So 12.7 into 10 raised to minus 3 meter. And if you solve this equation, the H will be comes out as 9.64 watt per meter square degree Celsius. Now we have the equation for the fin, which is isolated at tip, T minus TA upon T0 minus TA is equal to cos hyperbolic M into L minus X upon cos hyperbolic ML. So let's first find the M. So which is equal to under root of 4H by KD. So a value of H that we have derived, which is 9.64. K is conductivity of fin that is given in the given data, which is 54 watt per meter degree Celsius. Now here you can see that the D, which is the diameter of fin, which is 12.7 mm into 10 raised to minus 3 meter. We have the fin outer diameter over here, so which is 12.7 into 10 raised to minus 3. So if you put all this value, we will get the M is equal to 7.49 over here. Okay. So this is how you can find the M. So here apply this equation T minus TA. What is TA? TA is fluid temperature, which is 35 degrees Celsius. You already know. Now here T0. What will be the T0? So T0 at the base of the fin. That means here you can see that. So for our simplification, T1 is nearer to the base, of the fin. So that's why we are going to take T0 equal to T1 equal to 68 degrees Celsius over here. Now next, TA you already know 35. We have the value of L, we have the value of X. X means the distance at which we want to find the temperature, which is 8.2 centimeters, so which is equal to 8.2 into 10 raised to minus 2 meter. L is means total length, which we have 102 into 10 raised to minus 3 meter. So now if you put all this value, you will get the T, which is equal to 60.63 degrees Celsius. So this is nothing but the value of T5 by theoretical. So now let's go towards the conclusion. So conclusion. So let's see the conclusion. So you know that we got the practical value, which is 61 degrees Celsius. How you got this practical value? So that is already, if you put voltage and current, particular voltage and current to that device, you can directly read this T5 value from the reading, from the apparatus. But this theoretical value that we have derived, which comes out to be 60.63 degrees Celsius. So now here you can see that there is some margin between these two. Why? Because from the result of experiment, we can say that both practical and theoretical value differ by some margin. Why? Because due to the assumption involved in the theory of pain. Because when you learn that theory of pain, there is already assumption in there, which is not possible that it will remain same in practical condition as well. So that's why there is some difference between the value of theoretical and value of practical. Now, with the help of natural convection method, you can find out the temperature at any length of fin. So that is our second outcomes, and also you can find out the value of convective heat transfer coefficient. Okay, now same practical can be done by force convection method. So how you can do that for convection method? So you have already seen the image which is in our practical. So what do you have to see? What you have to do? So what you can do is just see the image of our practical. So it is something like this. So if you want to do it by the force convection method, then you have to start on the switch of the blower, so which is just below the ammeter. You can see there's one toggle switch over there. So if you have to just switch on the blower, and what will happen, the blower will be started and the air will be passed through the duct, so that forcefully the air will be passed through the duct. So that will become the force convection. But right now we have done this practical by natural convection method. So in natural convection method, no blower and no manometer involved. You have to just open this top cover and you have to take all the reading. Okay, so this is how you can do this practical. So this is the detailed explanation of our practical. I hope you will like this video. Have a nice day. Bye-bye.